All right, hello everybody. I appreciate y'all coming and watching this video here on inverses. So let's just jump right into it. Today we're going to be talking about how to prove that two functions are inverses of each other. Okay, so given two equations, you'll be able to say that yes, these are indeed inverse functions of each other. There's a specific way to how we do it. Now let's refresh ourselves on exactly what an inverse function is if we have an inverse function of another. Okay, so you probably already know this, but an inverse function pretty much just undoes what another function does. Okay, so like if you have this function and it does a bunch of crazy operations, multiplying, dividing, all this stuff, and we're going to get some answer. What an inverse function does is it takes that answer and undoes all the operations and takes you back to where you begin. So this is kind of what I tell my students whenever I'm explaining that. I'm like, let's say we have some generic like X value. Okay. Oh, and again, I apologize so much for my handwriting. I'm writing on an iPad and it's just very hard for me to do. So please be patient there. But let's say we have some generic X value and we plug this generic X value into a function, okay, which we've done for so many years now. Then we're going to get some Y value out, right? Well, what an inverse function does is it says, okay, an inverse function, f to the negative first of something. If I take that y value that I just got and I plug it into the inverse function, it's going to undo all those operations. It's going to undo all those operations, and I'm going to end back to where I started with x. Okay, that's what an inverse function does. And that's honestly how we're going to prove it. We're going to talk about the generic x and how it's going to map us back to where we began. So another way of this argument that I just said here, okay, see how I plugged y into the inverse function and it takes me back to where I started. Another way of saying y is to say f of x, right? So another way of writing this is that f inverse of, instead of y, I'll call that f of x equals x. Okay, that's the argument that we're making here. And honestly, that is the definition of an inverse function. That if I plug in some function f of x into an inverse function, so function composition, I may get some y value, but it's going to map me back to where I started at x. Okay, which is exactly how the proof is going to work today for proving inverse functions. But instead of just showing that f inverse of f of x equals x, we also have to show the other way as well. It has to be true both ways. They both have to map the function back to x. So today we're going to be doing both of these function compositions, and if both of these function compositions equal x, then those two functions are inverses of each other. Okay? So again, to prove algebraically that two functions are inverses of each other, we have to show that both of these function compositions equal x. Now, I have students in the past ask me like, well, I don't know which one's f inverse and which one's f. Well, they're both, if that makes sense. Like they're both inverses of each other. So you can denote whichever one you want as f inverse. That point doesn't matter. Okay? So let's look at an example. It says, prove that h of x and g of x are inverses of each other. Now, this brings up another argument that I'd like to talk about. I have had some students in the past that will take, like, say, for instance, the g equation, and then they will figure out what the g equation's inverse is following those steps, which we'll talk about again in a sec. And they'll be like, oh, that is the same equation as h of x, therefore they're inverses of each other. I get the idea behind that because you will or do know how to find an inverse function from any function, but that's not how you prove it, okay? Mathematicians are funny about how they like their proofs. So if you ever need to prove an inverse function, you have to follow these steps, okay? Um, in this particular example, instead of saying f and f inverse, you're going to have to show that g of h of x equals x. And we're also going to have to show that uh, h of g of x equals x. So plugging one function into the other is going to both give you x. Okay, so we'll kind of split this down the paper here if I can. Okay. We'll start with the g of h of x. Now, this is function composition. This is stuff that you should be comfortable with. This means that we're going to take the h equation and plug it in for x into the g equation, right? So instead of 1/2 x minus 5/2, this is going to be 1/2. Instead of x, we're plugging the h equation in, so it's going to be 2x plus 5. And then minus 5/2. Okay? So again, sorry for the terrible handwriting, but all I did there was plug the h equation in for g. Okay? Now we simplify it. And it should simplify down to x to prove that these are inverses of each other. So we're going to distribute the 1/2. 1/2 and 2x becomes x. 1/2 and 5 becomes 5/2. And I think this is a pretty simple little simplification here, right? 5/2 and negative 5/2 cancel out, and we're left with x. So far, we're good. Now, let's show the other way around. So we're going to take the g equation and plug it into the h equation. Okay? So h is 2x plus 5. So everywhere I see an x in that, I'm going to plug in the g equation. So that is 2. Instead of x, it's going to be 1/2 x minus 5. Or I'm sorry, 5/2. I apologize. And then plus 5. Okay. So a quick little simplification here. That's nothing terrible. 1/2 and 2 becomes x. Negative 5/2 times 2 is negative 5 plus 5, right? And those go away. So I'm left with x. Okay. So because both function compositions equaled x, that means both functions undo the operations of the other functions, and therefore they are inverses of each other. So the math isn't terrible. As long as you feel comfortable doing function compositions, you got this. Okay? Now, let's look at this next example real quick. If I can move forward. There he is. Okay, look. I want us to be careful with this. Find the inverse of f of x. So here's f of x. It's 2x plus 5 over x minus 3. Now, some of y'all might already know how to find the inverse of a function, and if not, it's no big deal. We can talk about this. But I want us to understand that this does not mean that you are proving an inverse function. You are just finding the inverse function. Okay. Well, let's refresh ourselves on the steps. You may know this already. You may not. Not that big a deal. But there's really only 2 steps. Number 1, if we say that this is y equals 2x plus 5 over x minus 3. Think about what an inverse function does, is it switches x and y. Okay, it maps one function back to the other. So the first step in solving for the inverse function itself is to switch x and y. So everywhere you see a y, you're going to plug in an x. And everywhere you see an x, you're going to plug in a y. Okay. And then, so that's step 1 is plug or is switch x and y. Now, number 2, really the last step, is just get y by itself. You want to get it back to like some f of x or y equals equation. There's 2 y's here, but it's not terribly hard to do. You want to start by multiplying both sides by the denominator. I'm trying to squeeze this in here. You can tell that. But I'm left with y minus 3 equals, oh, I'm sorry, y minus 3x equals 2y plus 5. Okay, and then we're going to distribute the x. We're going to get xy minus 3x equals 2y plus 5. And at any point, I encourage you to pause the video and try this on your own if you can. But it's the goal is to get y by itself. So my suggestion is to always get all of your y variables to one side and everything else to the other side. So what I'm going to do is I'm going to move 2y over here and negative 3x over here. So what we got is xy minus 2y equals 5 plus 3x. Okay. And then if we're trying to get y by itself, notice that these two have a GCF of a y. So this is how we go from two y's to one y. We're going to take that GCF of a y out. So then I'm left with x minus 2 equals 5 plus 3x. And then the last step would be to just divide by x minus 2. So my final answer here is y equals, I'm moving to the top here, y equals 5 plus 3x over x minus 2. Okay. Now, so that would be your equation. Technically, we instead of y, we will probably want to use the correct notation here, since we're considering this the inverse function. We'll change that y to f inverse of x, just so people know that this means the inverse function of what we started with. Okay. So there you go. There's the inverse function, and here is the original function. So we got these two functions, 2x plus 5 and x minus 3. Okay. Now, we didn't prove that one was an inverse of the other. We just found the inverse. So part B here, I want us to actually prove that what we found are indeed inverses of each other. So this is a common second question to finding inverse functions. Now that you found it, like we know that they're inverses of each other, but let's actually prove it. All right, let's actually prove and show that they were. So let's refresh ourselves. F of x that we started off with, and in fact, I'm going to have to go back and look, was 2x plus 5 over x minus 3. 2x plus 5 over x minus 3. Okay. And the inverse function that we found was 5 plus 3x over x minus 2. 5 plus 3x over, make sure I get this right, x minus 2. Okay. So again, it's terrible handwriting, I know, but there's the original function and the inverse function. So if I want to show that one is the inverse of the other and vice versa, we have to do both function compositions. So let's do it. Let's see what happens. Let's have some fun with it. Let's start off with the first one. F of f inverse of x. Okay. So what that means is I want to take the original function, this first function right here, and I want to plug in 5 plus 3x over x minus 2 everywhere I see an x in this equation. So it's going to look kind of ugly, but the simplification is not the worst. Okay, so this is going to be 2, and instead of x, we're going to plug in, ready for this, 5 plus 3x over x minus 2, and that is plus 5 over, and instead of x minus 3, this is going to be 5 plus 3x over x minus 2 minus 3. So that may look ugly, and because it is ugly, okay? This is a complex fraction. Now, to simplify this complex fraction, again, the idea is that it's going to simplify down to x. You can do it any number of ways that you like. There's actually two really ways that we can do this. Now, the way that I teach my students, and I don't know how much y'all have dealt with complex fractions in the past, but remember, complex fractions are fractions like that within a fraction. I call it fraction inception. Okay, so we got this smaller fraction operation in this bigger fraction operation. What I tell my students whenever doing these problems is look at the denominators of all the little fractions. Okay, so it looks like we got x minus 2, 1, and x minus 2, and 1. And I tell them how the best way to simplify this would be to multiply the top and bottom by the lowest common denominator, what they all share in common. In this case, that would just be 1 and x minus 2. So I'm going to say x minus 2 over 1 on top and x minus 2 over 1 on bottom. Okay. Now, again, some students prefer to simplify it as one fraction on top and one fraction on bottom and do same, change, flip, all that stuff. I prefer to simplify it down to one fraction, okay? So all you do is you're going to multiply the x minus 2 through to both the quantities. And what's going to happen is the x minus 2 is going to cross out the denominator with this x minus 2. So what you're left with is, and here, watch what I do here, 2 on the outside, and the x minus 2 and x minus 2 cancels, so you're left with just 5 plus 3x. And then 5 over 1 times x minus 2 over 1, nothing in the denominator cancels, so I'm left with just simply the tops multiplied together to 5 times x minus 2. And on the denominator, if I were to multiply through these two fractions together, in the first set of fractions, the x minus 2 on top and the x minus 2 on bottom cancel. So I'm left with just 5 plus 3x minus, and then 3 times x minus 2, right? There's nothing that cancels about that second part. Okay. So that's just a little reminder on how to do complex fractions. Now, I'm trying to keep this video short, so we're just going to kind of do this simplification kind of quick, and you can probably simplify it pretty good from here. But if I distribute the 2, distribute the 5, and distribute the 3 on all these quantities, you get 10 plus 6x plus 5x minus 2, or I'm sorry, minus 10, apologize, all over 5 plus 3x minus 3x minus 2. Okay? And again, just messed up. 3 times 2 is negative 6, not negative 2. You got to distribute everything here, Forbes. So there you go. That's 10 plus 6x plus 5x minus 10 over 5 plus 3x minus 6. Now, the idea is it's going to simplify down to x. Look what happens. 3x and negative 3x go bye-bye. 5 minus 6 becomes negative 1. So on the denominator, I got negative 1. And on top, I got, let's see here. And once again, my multiplication is off today. I apologize. Negative 3 times negative 2 is positive 6. Positive 6. So on bottom, it's 6 and 5 is positive 11. Sorry about that again. My mental math is awful. All right, but on top, we have negative 10 and positive 10 are canceling, and we're left with 11x on top. And 11 and 11 cancel, and I'm left with x. Okay, so the one way, plugging the function in, the inverse function into the function, you get x. Now let's do the reverse and show the same. So what I'm going to do is I'm actually going to copy this over to a new slide for space. Okay. All right, so we showed one way already. Now let's show the other way. That's taking this function here and plugging it into this function here. So we need to show f inverse of f of x. Okay, so what that looks like is everywhere I see an x in the inverse function, I'm going to plug in the function 2x plus 5 over x minus 3 divided by, instead of x, it's going to be, again, 2x plus 5 over x minus 3 minus 2. Okay. Now, we know this is going to get down to x, but again, it's all about how you like to simplify it, okay? Some students like to get one fraction on top, one fraction on bottom. Again, my biggest bit of advice when dealing with complex fractions and what we do in calculus is we multiply the top fraction and the bottom fraction by the common denominator. Okay, the common denominator between all these little things, between 5 and, like, we got 5 over 1 technically right here, and 2 over 1 right here, and 2x plus 5 over x minus 3 and over x minus 3. Between those four little quantities. The GCF, or I'm sorry, the lowest common denominator is x minus 3. And we're going to say x minus 3 over 1 divided by x minus 3 over 1. So, I mean, you know, technically x minus 3 over 1 and x minus 3 over 1 does reduce to 1. So we're not changing the value of the problem. But what we're doing is we're going to distribute this value through to each of these terms. Okay. And when we multiply fractions, okay, multiply straight across, right? So if I do that first one, like 5 over 1 times x minus 3 over 1, nothing cancels, but we're left with just 5 times x minus 3 plus 3 times. Now, if I multiply this across to each other, the x minus 3 and the x minus 3 cancels, so I'm left with 2x plus 5. And on the denominator, the x minus 3 and the x minus 3, if I multiply that across, they cancel. So I'm left with just 2x plus 5, and then minus 2. And then the x minus 3 doesn't cancel with anything with that quantity, so we're left with that. Okay? Now, again, that's just my suggestion for dealing with complex fractions, is multiplying by that lowest common denominator. Okay? And we're going to simplify again, so we're going to have 5x minus 15 plus 6x plus 15 all over 2x plus 5 minus 2x plus 6. Okay. Now we're going to see something similar as before. The 2x and the negative 2x cancels, so on the denominator I'm left with 11. On top, the negative 15 and the positive 15 cancels, and I'm left with 11x, and the 11 cancels, and it does end with x. Okay, so that was a long example, but I like this example because it proves a point. Look, 2 slides ago, we found the inverse functions, okay, and that's old math. We should know how to do that already. But then the new thing is we proved that that was right. We proved that by doing function composition. Now, I apologize that the function composition was a little ugly, but it was good. Okay, I mean, it was a good practice of complex fractions. Okay. Now, if you didn't like that, let's do one more example, and we'll be done for today. Okay, you have a little worksheet to practice after this, but for now, we'll just end with this. Number 2 says, find the inverse. Okay, we'll do that. And then we're going to prove that they're inverses of each other. So very similar to what we just did. So let's start by doing this. Start by saying, okay, step 1, we're going to switch x and y. So I'm going to say x equals the square root of y minus 4. And then we're going to get y by itself in that second step, right? So I'm going to square both sides and add 4. So I get that that y equals x squared plus 4. Or we'll call that f inverse of x, and we'll say, all right, that is x squared plus 4. Now, if I want to prove, okay, if I want to prove this, you need to show 2 things. You need to show the function composition both ways goes down to x. So let's start with f of f inverse of x. I'm going to try to squeeze this on one slide so you can see them side by side this time. Okay, I don't think this is as bad as the last one. So what that looks like is everywhere I see an x in this original equation here, I'm going to plug in x squared plus 4. So that's going to be the square root of x squared plus 4 instead of x minus 4. And that's so much easier than the last one because look, 4 minus 4 cancels, and you're left with the square root of x squared, and the square root of anything squared is just what you started with. So that function composition simplifies down to x. What about the other way around? What if I do f inverse of f of x? So the reverse. What if I plug the original function into the inverse function? So everywhere I see an x in this equation, I'm going to plug in the square root of x minus 4. So that's going to be the square root of x minus 4 squared plus 4. Okay, well, if you square a square root, it cancels it out. And then -4 and +4 cancel. And then I'm left with x. So I think you probably like this example a lot better than the last example, but the point is it summarizes everything that we just did, okay? You should know how to find an inverse function. So you should know how to do this piece right here, okay? That should be an older lesson. And the new lesson is how to prove that those are inverses of each other. So it's all about function composition, plugging one into the other and simplifying them both down to x. Okay, so you have plenty of practice to do. I appreciate y'all watching this video and spending time with me, and good luck. If you have any questions, you have plenty of teachers that are willing to help. So I wish y'all the best of luck. Thank you. Bye.